Okay, looking in section 2.6 now, we want to work question 20, and it says to look at the limit as t goes to 0 of the sine squared of t over t. Now, when you do a direct plug-in, well, first of all, I always encourage students when they're thinking about this sine of squared t, think of that as the sine of t squared over t. So remember, that's just a notation there. And when you do a direct plug-in, you do get 0 over 0 because the sine of 0 is 0, squared would be 0. So if you go to y equals here, let's just get an idea of what this graph might look like. So if I do sine t, and then I square it, and then I divide by t, and I look at the graph, it does appear that as t goes to 0 from the left and the right, the y value is 0. You could also look at the table, and these are numbers to the left and right of 0, and notice that the y values are very close to 0 as well. This 9.99 e to the negative 4 means move your decimal to the left 4 places. That's scientific notation, so it's a decimal and then 3 zeros. So that's very close to 0. Okay, so it does feel like the answer is 0 when I look at the graph and then also the numeric. So just verifying it with our calculus, or this theorem that we've learned this time, what we can do is we can write sine squared t over t as the sine of t times the sine of t, and we can divide that by t. And now we can think of this as two separate products here. Notice sine t over t, if you think of the limit as t goes to 0 of sine t over t, we proved that that was 1. So these limits both exist, so we can use the basic limit laws to write this like this, because both of these limits exist. And then when you plug in 0, we know that this limit when you plug in 0 is 1. The sine, we know that when you plug in 0, the sine of 0 is 0. And when we plug it, we know by, we proved that the limit as t goes to 0 of sine t over t is in fact 1. So this is 0 times 1, which is 0. So that works to make the sort of a careful argument as to why that limit is in fact 0.